Okay, let me see. Let me put this if F5, right? The full screen. Ah, yeah. So I will be running in parallel both screens because, of course, this course is called Renewable Energies. For any reason, my computer camera here looks very blurry, and I think it's because a coffee fell in the computer a few days ago. I was drinking, it fell. I saw the computer, drank coffee also. Then I explained already what's the purpose of the class. I will be talking about many things simultaneously because this is an introductory class. Then let's go to what is energy. Energy natural is the capacity to do some work. I will share these slides, of course. Energy can be useful or useless. I think you need the lion, maybe. Lion. We talk about this useful energy or useless. How do you measure the energy useless or useful? Entropy. 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 I will give you a basic example. There's a construction there in front with the bamboo, which is now a polemic because of what happened in Hong Kong. But let's say those machines, they invest energy, in the construction of a building. A building is a well-organized structure, but that energy becomes useless, no? Once it's invested in that, it dissipates, it goes to where? It disappears. Example, a truck comes, take the sand and do this. So what happened with that energy? It disappears or what? It's converted in other kinds of energy. Part of that energy is dissipated in heat. Heat. If you sum all the types of energy, the potential energy of the sun or the energy, whatever, plus whatever, then you get that the energy is conserved. There is no violation of the energy conservation. Only that the processes are not ideal. No. Now, what happens is that when you organize this, the entropy of the building reduces, but the global entropy, machines plus building, increases. No? So the global entropy increases. That's a way to measure the degradation of energy. That's called irreversibility in thermodynamics. It's a concept which we couldn't revise in the course, elementary course you saw, but at least we saw entropy. What is entropy? Energy can be stored. How do you store energy? Imagine a string. Remember the string? I put a string compact like this, and I block it. The string is like this, very tense. That's energy stored in the string. It's elastic potential energy. Once I release, the string goes. That's a way to store energy. Very basic, no? Another way to store energy, I put this thing at the top. It's storing gravitational energy, of course. And once I release it, it becomes useful energy. So potential energy by itself is not useful. Well, it's a store. I mean, it's useful in the sense that I can use it later, but at the moment you are not using it. That's why it's called potential energy. That's why the name is potential. Right. Uh, the theory of war and energy, I would like to revise it here. And for that purpose, I want to open this link here. Uh, this one here. And then I will open it here also in this computer because I am recording here. No? Then I have to do a new sharing here. So in this case, we can see that when you push a block, basic, you are doing some work. That's a way to invest energy in the block. Work is energy at the end of the day. When you go to the gym, some of you are fanatics of going to the gym. I don't know if you go to the USJ gym, but whenever you carry something, you are investing some energy there. So there is exchange energy. The energy which your body carries is becoming, it's storing in the iron, no? Which you carry. So we saw the concept of work. Work is force times the distance in the direction of the force. So it's a dot product actually in the vectorial sense. In this course, probably I will see later if there are problems or no, or if we just talk globally about the concept. But ideally, you should know this. Work, force, and distance. For example, if I apply a force in this direction to 20 degrees, the work I do for over this block is the force applied multiplied by the distance. The force applied in this direction, in the horizontal direction, multiplied by the distance. And of course, when I do work over an object, I am exchanging energy or I am storing energy somewhere. Okay. But there are losses in that process. This is another example of energy. The batteries have chemical energy which is converted to something useful. And for example, when you have a hammer, when you're doing this to some surface, kinetic energy is becoming what? When you hit, what kind of energy is converted into when you hit? The vibrations, some kind of kinetic, but kinetic, different kinetic, not the vibrations of the molecules of the surface you are hitting. But that energy is useless. I mean, the useful is the one you are doing that. The other is useless. It dissipates over over the surface or over the volume of the body. So the unit of energy is the joule. I think this is basic. You should know. The joule is the basic unit of energy. Joule is Newton times meters. Uh, Sometimes I see guys who do research and they don't put the units. Some guys do research and they make plots and they don't put the units of the axis. They don't put the horizontal axis is this unit, the vertical axis. People have to guess. Then it's important to specify the units. Dimensional analysis is important. It's something I was teaching recently to the PhD people, actually, in one course. This is potential energy. Look, the potential energy is nothing else than the work that the gravitational force do over an object. When the apple falls 1 meter, the gravitational force is mass times gravity, no? And if you multiply by 1 meter, it gives you the work, the work that the gravitational force do. And it's exactly the potential energy the apple has, 1 joule in this case. 1 Newton multiplied by 1 meter, 1 joule. Then, of course, this is an explanation of the units. I will share these things. In any process, there is an efficiency to measure. The efficiency of any process is the useful energy divided by the total energy you invest. Let's assume you invest 200 joules in a process, but you only could use 100. Then it's 50% efficiency. But now, I think if you study thermodynamics very well, you should know that there's an ideal efficiency, especially in thermodynamic cycles, refrigeration, these kind of things, which I will explain later, probably in this class. I don't know if there is time for that. But you should know that there is a Carnot efficiency, no? Carnot efficiency, which is the highest possible efficiency in a thermodynamic process. And not even the highest efficiency in a process is 100%. So in reality, when people go to thermodynamic process like refrigeration, which use COP, actually coefficient of operation or efficiency, or engines like cars, engines, or planes, they don't use this formula you see here. This formula is not the one they use. Of course, they use this. They might use this, yeah, but they compare it with the Carnot efficiency because not even the Carnot efficiency is 100%. Let's say the Carnot efficiency is 50%, so you get 45% is quite good. Wow, you are so close to the Carnot efficiency. But if the Carnot efficiency cannot reach even the 100%, you cannot expect to overpass that efficiency. So it means if Carnot efficiency is 50 or 40%, this is the highest you can do, the best you can do. We will see that later. So not even the most ideal processes in the thermodynamic cycles give you 100% of efficiency. That's something very important because actually it's called, if the memory doesn't fail to me, it's the Clausius theorem. It's a Clausius theorem. Clausius was a guy. It's the family name of somebody. Because otherwise you could construct a perfect machine, and perfect machines don't exist. Every machine has a waste. When the machine comes, a normal machine operates like this. I will put on the board here. A simple diagram of a machine is like this. You have high temperature here. You have low temperature here. You have an engine here. And the heat goes from high to low. And it makes some work, useful work. And the fact that you're wasting here some heat, it means that you cannot use all the energy. So your efficiency, even if you assume all these processes ideal, it will not be 100%. So there is no perfection in thermodynamics, basically. Then, of course, but this is too premature to mention right now. So now let's go back to the slides. I go back to the slides. Share here. And I go back here to the slides. Then types of energy, I will mention some. There are many, of course, but let's talk about the kinetic part. You can find this in Google for sure. I think Google would not lie in this, but of course, we have to go deeper than Google. Kinetic energy is very general. The molecules, when they move, they scatter, they have kinetic energy, they collide to each other. That generates dissipation by heat. But they also have potential energy because they vibrate. They are like strings vibrating. So we have thermal energy. The vibration of atoms and molecules is somehow kinetic, but it manifested at the end heat. It dissipates as heat. Electrical energy, the electrons move. Well, not only the electrons, the ions, for example, if you have salt, you throw salt in the water. Salty water, it has free ions. So some molecules get release electrons or whatever, and they remain charged, no? So those are free charges. If you put a voltage, those charges move. So the electricity is transmitted by any charge. It doesn't have to be electrons necessarily. What happens is that the electron is the easiest, of course. It's the easiest. That's why the metals has a layer of free electrons. They transmit the electricity very easy, very easy. You put a voltage, you touch it and use immediately. But take this glass. For example, compare this spoon with this. What's the difference between this spoon and this thing? Somebody can tell me? This is a metal, this is not a metal. This is a ceramic. Ceramic. The same ceramic they use for the spaceships, actually, for covering the surface. Then, what's the difference? This guy has free electrons. This guy doesn't have free electrons. Or maybe one or two or something. not so many. If I put a voltage between these 2 points, I will feel the electricity flowing easily here because these guys, they have a bunch of free electrons on the surface. So the electricity will flow through the electrons. The electrons will move. Negative charges moving. Negative charges moving one direction is like positive charges, positive current moving in the opposite direction. This is how we study the current. Remember, the current is flow of negative charges in general. In the most basic aspect, when the electrons flow in one direction, let's put it here, because I see confusing faces. This is a ball. Yeah. The electrons, if an electron moves in this direction, then it means the current is moving in the opposite direction. Because the current represents positive charges. Then if a charge negative move here, you can assume mentally that positive charges are moving in the opposite direction. So the point is that this guy has free charges, this has free electrons, the electron move. This not. I put a voltage here between these 2 points here, and maybe I touch, I don't feel anything. And the reason is because nothing is flowing. Nothing is flowing. Or it tries to flow. It tries to flow something. Maybe the molecules start to vibrate. Maybe you feel that it becomes hot. That's why you know that there are some devices that you connect here via USB and you put this glass and this glass can warm a little bit. But of course, if you touch, nothing happens. Because it transmits, it's that it doesn't transmit, it transmits electricity, but very inefficiently. Very inefficiently. It's vibrations of the net. And those vibrations, they obviously are not so efficient. Then this is something important. We have radiation. What is radiation? Tell me an example of radiation, naively. Radiation.
Light. Gamma.
Light. Gamma also. The UV, ultraviolets. So I will ask you questions naively because you should know this. Why the sky is blue? What is the color of the sunlight? The light of the sun, which color? Is white. It's white. It combines all the colors. So when you combine all the colors, it comes out white. No? So why the sky is blue then? Yeah, more or less, yeah. And then what happened? I mean, if we analyze the visible spectrum, the spectrum of radiation is, I don't know if I had it here. Let me see. No, probably I didn't put it here. But we'll see that later. The spectrum of radiation has ultraviolet, has radiation that we don't see. We cannot see ultraviolet radiation. We cannot see gamma rays. We cannot see dangerous radiation, which generate cancer. The X-rays, when we go to test our bodies also, those rays are dangerous. If you expose too long time, you can get a cancer or something. It destroys your cells because it has too much energy. The energy is too high. But there is a narrow region of the electromagnetic spectrum which you can see. And there is a lower energy radiation that we cannot see neither, which is the radio waves. Radio waves we cannot see. The waves of radio are very inoffensive. A very long wavelength, have low energy, we cannot see it. But there is a narrow spectrum. It goes from blue to red. Blue is the highest energy, and red is the lowest energy region of the spectrum. Now, of course, when the sunlight arrives the atmosphere, it starts to block the dangerous rays, UV, all these kind of things. And in the middle also blocks the blue. I mean, that's part of the reason why we see of course, it scatters the blue everywhere in the atmosphere, and then we see the sky blue. This is more or less the reason. And then, so of course, the sunlight at the end we see between yellow to red, more or less. Sometimes red, no. And red is very inoffensive. So I was just curious to see how much you know about these general issues. But anyway, radiation has a quality. It's different to all the other energies. All the other energies require a medium of propagation. When I do this, the vibration it propagates to the table, the waves, mechanical waves. I do this, the energy of the wave propagates. In the fells, with the city farms, the wind collide the fells and the fells. The trees move. That's like a wave. But what is the quality of electromagnetic radiation? It doesn't require a medium of propagation. It doesn't require anything. That's why we can see the stars. That's why we can see everything. Then, of course, the the point here is that that radiation will be fundamental because heat transfer. We have heat transfer via radiation. That's why the nuclear bombs kill us, actually, because of the heat of radiation. And of course, radiation itself, uh, in small fractions, can kill us also in the long term. But as also excessive heat can be transmitted via radiation. And we will see later the mechanism. But the key point, what I want to summarize, is that radiation doesn't require a medium of propagation. Even if I made this room empty, no air, nothing, I will still see light. I will see the light and still the waves of radio and the dangerous and non-dangerous radiation will propagate. And they carry energy. That's why they kill us. That's why radiation can kill us, because it has energy. Then, of course, when the radiation hits our body, if it has too much energy, it can create some transmit that energy to our cells, and it's too much to our cells and disintegrate our cells or something. So that's something to take into account. Some energy, the sound has energy. Why? What happened when I talk to you? What do you listen? Vibrations of what? Molecules of the air. Yeah, the molecules, what you feel is the vibration of the air. If I empty this room and there's no air, assuming that we don't die because there's no pressure, we need this pressure to live, actually. The atmospheric pressure, we need it to live. That's why the cabins of the planes are pressurized. But let's assume that we have some dresses, whatever, special like astronauts. There's no air here. We vacuum, we make a perfect vacuum here. If you talk to me, I will not listen to you because there is nothing vibrating. Then how can I listen to you? I will have to use a radio because the radio waves, they can be transmitted in vacuum. The radio waves can be transmitted. That's why these guys, even to radio, they can still communicate. But if you talk to me like that in vacuum, these movies of Star Wars that they shoot a gun and there is a sound, this is not like that. You will not listen anything at all. Only the impacts in your ship, boom, because your ship is pressurized inside. So you will feel the vibration. So the point is that the sound has energy. That's why sometimes you feel tired when some people are too noisy. Particularly, I think with the age, sometimes people cannot listen well and they try to talk loudly. And then sometimes you feel tired not listening because it's too high. Or when somebody put the volume of the devices too high, it also makes you feel tired. And the reason is the energy carried, which has other conversions in your body, which I will not discuss here because it's quite complex, that conversion. And of course, motion energy, objects, wind, car, whatever. That's part of the ordinary kinetic energy we know. So kinetic energy, the most basic is the pendulum. I think everybody is familiar with the pendulum. The pendulum is the perfect conversion between potential energy to kinetic. For example, here, the pendulum stopped moving. Zero velocity here, zero speed. But it has potential energy. This potential energy converts into kinetic. And here, if we put the reference here, there is no potential, all is kinetic. Now, if the pendulum is perfect, this keeps oscillating forever. But ideally, no. But in practice, of course, it stop moving in the long term because there are dissipations of energy here in this part. it becomes heat. Heat. It becomes hot in the long term. You touch it, it can become hot, but not that hot. Then maybe you feel you need a perfect device to try to. I think, of course, technically I should give a break, right? The breaks are 4:30, right? So anyway, let's stop here, and I will continue. Uh, uh, 5 p.m. 5 p.m. is okay.
Okay.
Then let me stop this.